So thank you very much, Matteo, for the very kind introduction. And we have indeed worked together for quite a while, and actually I learned everything from Matteo as it pertains to self-interaction corrections. So what I'm going to do today is to go back to those fundamentals and explain some of the basic concepts of Koopmans functional that are electronic certain methods that go beyond DFT, beyond the quantum density functional theory approximation, in order to calculate the electronic structure of materials. So I'm very happy to be here at this Hubbard and Koopmans functional school, using linear response and quantum espresso, and very much thank Nicola Colonna, Matteo Boccioni, Andrea Ferretti, and Nicola Marjorie for bringing us here in this beautiful place. So this work was done in collaboration with them, and also in close collaboration with Giovanni Borghi, Shulwan Park, and Lin Nguyen, as well as the most recent development of Edward Linscott that I just met this morning. Was very happy to get a chance to meet him for the development of the latest implementation of those Koopmans functional. So before I tell you more about those newly released functionalities, I'd like to step back for a moment and talk about the motivation that underlies the development of those functionals. So in many areas of material science, we're interested in electron transfer, we're interested in understanding light absorption at materials or at interfaces. For example, here this is a photoactive heterojunction that is buried in the organic solar cells. And here the question is to be able to calculate the energy levels of the donor molecule and acceptor molecule in order to understand light absorption by the donor molecule, and then how an electron can possibly jump from the donor to the acceptor. This is also relevant in the field of photocatalysis, where we're interested at the ability of semiconducting nanoparticles to split water once they absorb solar light. And so here, what we need to do is to understand the light absorption properties of the semiconductor and understand the condition under which an electron can jump from the valence band, the conduction band of the semiconductor to the accepting level of water. So essentially, you want the redox potential of water to be below the excitation level of the semiconductor. And so an example where this is critical, this is a recent work with Matteo Boccioni and Yuri Timrov, in which we develop a computational material screening process with a tight co-validation between experiment and theory in order to accelerate the discovery of new photocatalysts, starting from a large number of semiconducting materials. And here you can see a high-level view of this 8-step process, and 3 of those steps, the prediction of the solar absorption, prediction of band alignment, and the correction of the band gap, involves electronic structure method that go beyond density functional theory. And to be able to accurately predict the performance of those materials, you need accurate electronic structure method. And so the goal of this work here is to tell you about those developments and tell you about some of the limitations of the method that exists. So many of the electronic structure methods that we have are based on density functional theory approximations. And one of the critical limitations of those approximations, as it pertains to predicting electron transfer and the solar absorption, is related to this lack of piecewise linearity. So as you can see here, the energy as a function of the electron number should be piecewise linear, and this was demonstrated in the work of Perdue, Parr, Balduz, and Levy, that essentially argued that anytime you encounter a quantum system with a fractional number of electrons, let's say you are in this region here, that system has to be a linear combination, a statistical mixture of two pure states. So those pure states are actually states with an integer number of electrons. And as a result, the energy for fractional number of electrons should be the linear connection of the energy of the pure state, of the state with integer number of electrons. And as a result, the energy should be piecewise linear with derivative discontinuities are integer electron counts. Okay, so this is an important condition that also relates to the delocalization error in DFT. So most of the functions that we have do not fulfill this piecewise linearity and instead are convex or piecewise convex. And as a result of that, often you would encounter a situation where at some point the slope becomes positive, okay, or zero. And this is where you're going to encounter the localization of the electronic charge. And this is also related to the instability of negative ions within density functional theory. It's also responsible for the underestimation of the band gap that we have heard about repeatedly in this workshop. And to explain this, it's useful to write a few equations. So I'm writing here the fact that the energy should be piecewise linear. So essentially, whenever you have a fractional electron number and you increase the occupation of the frontier orbital, the second derivative of the energy with respect to the occupation of that frontier orbital, essentially the HOMO, has to be equal to zero. Then what you can do is write Janak's theorem that tells you that the energy of an orbital, epsilon n, is nothing else than the derivative of the total energy as a function of the occupation of the orbital. So essentially, the energy of the orbital is the chemical potential of an electron in that orbital. And then by using those two equations, you can write this important relation, the Koopmans condition, that the derivative of the orbital energy should not change with the occupation of that orbital. If it does, it means that somehow the orbital interacts with itself. And if this condition is fulfilled, it means that the functional that you have is self-interaction free, meaning that occupying an orbital will not affect the energy of that orbital. So what happens in DFT, in the standard semi-local GGA or local density approximation, is that, as I said, you have that convexity. And because of that convexity, the derivative is positive, meaning that as you fill an orbital, as you increase the occupation of an orbital, what happens is that the energy of that orbital is going to increase. And so now if you try to predict the experimental electronic band gap, what happens is that the valence states are going to be occupied. So they are in a region where this epsilon will be overestimated because of the increase of the orbital energy as a function of the occupation. And conversely, if you look at the conduction band, the occupation is zero, meaning that in that case, you're going to underestimate the orbital energy for that specific state. And as a result, the orbital energy will be too low. And as a result of this increase of the orbital energy as a function of occupation, you're going to have a decrease in the band gap. So this is the connection between the underestimation of band gap and the self-interaction error that is directly connected to the piecewise linearity. So as you can see here, we can look at this effect by plotting the computational band gap as a function of the experimental band gap. And you can see that the band gap that is predicted by semi-local generalized gradient DFT is systematically below the parity line, meaning that you have an underestimation of the band gap for many of the compound semiconductors. Okay, so this illustrates the connection between self-interaction error, the lack of piecewise linearity, the localization error, and the underestimation of the band gap. So now the question is, how can we look at this in terms of the electron transfer between the donor and acceptor? So same effect here. So you have essentially an electron that jumps from the left to the right. Q denotes the amount of charge that is transferred from the donor to the acceptor. So you can plot the energy of the donor as a function of Q, and same thing for the energy of the acceptor. And because of the convexity of this energy, you will realize that the total energy of the system of this donor-acceptor pair shows a minimum at fractional transfer of electrons. So it means that at equilibrium, within standard DFT calculation, you will find that the electron will be split between the donor and acceptor. Maybe you will have here 65% of the electron on the acceptor and 35% of the electron on the donor. But if you fulfill the condition of piecewise linearity, then the total energy is a constant, and then the minimum is going to happen for full electron transfer as you expect physically. Okay, so that's again is one of the consequences of this self-interaction problem when it comes to predicting electron transfer between two fragments of a system. So this problem is actually not just related to DFT, but it's actually very general. Anytime you have an effective field approximation, you're going to encounter that issue of self-interaction. And I'm going to illustrate that on the simplest possible model that you can think of. And this is the model that was taught to me by Matteo, the Hubbard model that you have heard about yesterday in the degenerate band limit. And I'm going to talk specifically about the Hubbard model within the zero configuration width approximation, in which all of the electrons have within a given level have the same energy. And the outcome of this model is essentially a Hamiltonian that is written like this, and that is reminiscent of the expression that you have seen yesterday. So to explain the model, I take here the simple example of copper oxide. So I have some copper 2+ in a D9 electron configuration. And for the sake of illustration, I take here the simple case where 4 of the orbitals are fully occupied by the spin up and the spin down, and the last orbital is occupied by half spin up and half spin down. So within the Hubbard model and within this zero configuration width approximation, all of the orbitals individually have the same energy, that is called epsilon. And there's also this electron repulsion parameter. It's the energy of a pair of electron U that essentially tells you what is the energy cost of having 2 electrons on the same copper cation. So I can take here this example. So you can use an effective counting. So you have an effective theory in which essentially you say I have 9 electrons. So you put 9 here, and you just count the number of pairs. So you have 9 electrons. It makes you 9 times 8 divided by 2 pairs, 36 pairs of electrons. And as a result, you get 36U as a contribution to the energy. So this is the result of a very global counting of the number of pairs from the distance. But if you refine this model, you can look at more refined pairwise counting of the interaction, and you can count how many full spin pairs you have, and you have 8 times 7 divided by 2. How many half spin, full spin pair you have? So in that case, you have 8 times 2 for each one of those. And how many half spin pairs you have? And that's only 1 pair. And as a result, you see you have a slight difference that is of 0.25U. That is the difference between the effective counting, like you do in density functional theory, and the more refined pairwise counting of the electron interaction. And so the correction will be a quarter of U in that case. So we can formalize this a bit more, and now we can essentially write this in terms of the spin occupations. So this is the total number of electrons. This is the effective counting of the number of electrons. Then you can do the more refined counting, and in which you see, instead of having the number of electrons minus 1, is the number of electrons minus the occupation of the orbital of interest. So if you take the difference between those two, you get exactly the correction that was discussed yesterday. And it's essentially the difference between having a effective counting of the interaction, very global, and looking at it at a more pairwise manner. Okay, so then we can illustrate this like in the following manner. So the effective counting method gives you n and a parabolic term that depends on n, the total number of electrons. So you get this parabola here. And if you do the pairwise counting, you get this blue piecewise linear curve. And the difference between the two are those pieces of concave parabola that is the essence of the U correction. Okay, so this is, I would say, the simplest model in which you see the emergence of self-interaction error when you deal with an effective field approximation. So thanks to Yuri and Matteo, it is now possible to calculate this U parameter using linear response theory that greatly simplifies the application of this method to solids. So essentially, the U is nothing else than the curvature of the energy with respect to the occupation of a given atomic orbital. This expression involves the derivative of the effective potential, because we're dealing with an effective theory that we would like to correct with respect to the charge density. So you have here a non-local operator. And the second non-local operator that is involved is the dielectric constant that essentially accounts for orbital relaxation and orbital spinning effect that is extremely important if you don't want to overestimate this correction. So recently, my student Nicole Kirchner has done, based on this implementation by Yuri and Matteo, an extensive benchmarking, looking carefully at the convergence with respect to the wave vectors, looking carefully at the convergence with respect to the number of iterations of calculating the U, relaxing the structure, calculating the U, relaxing the structure. And we see that after 4 iterations, this converges. Importantly, she used orbitals that are orthogonalized using the Lodwing approach, and applies this to not only the d orbitals of open shell heavy metals, but also on the S and P orbital of the light element. And this turns out to be critical to get this type of accuracy. So you see on this benchmark that contains chalcogenide, oxynitride oxide, we get a fairly good agreement between the computed band gap and the experimental band gap, with a slight tendency to overestimate the band gap. So this is probably the result of having fixed orbital, and because of that, of over-localizing the electron and overestimating the self-interaction corrections that we have in that case. More recently, we did a full self-consistent study of other conductors that are relevant for photocatalysis. So again, the same observation. After 4 iterations of the U, so these are the 4 last bars, you converge, and you have a tendency to overestimate the correction, probably because of the rigidity of the atomic orbital that you employ. The result compares favorably with hybrid functional, with an error that is brought down from 1.5 to less than 0.5 EV as you employ the new correction. But while the HSE 06 functional gives you an error of 0.6. So here we have a good compromise in terms of computed cost and accuracy. But again, we have this tendency to overestimate the band gap. And so the question is, can we do better? So in that case, it's extremely powerful, because we can use that and do material screening. An error of 0.5 is more than enough to screen for photocatalysts. But there are cases, for example, when you're interested in the polarizability and hyperpolarizability of system, where you're interested in the actual localization of the electron, where the ability to directly operate on the self-consistent orbital will be beneficial. And this is what motivates the development of those Koopmans corrections to self-interaction errors. So Matteo is the one that really sat down and explained to me this Hubbard model, on which then you can have the ability to extend and apply the corrections not only on atomic orbital, but on actual orbital that you have in the course of the self-consistent minimization. So again, this is the curve that I was presenting. So what we have is this nonlinear trend that we can characterize using a Slater integral. So according to the Janak theorem, the energy is the derivative, the orbital energy epsilon is the derivative of the total energy. And as a result, if you integrate this from 0 to the occupation of interest, you're going to get an estimate of the energy, and this is what is going to give you this behavior. But what we want is a linear behavior, where essentially the energy is given by a coefficient that multiplies the occupation of the orbital. And this coefficient, in one flavor of the Koopmans approximation, is nothing else than the derivative of the energy midway between two integer numbers. And so we take typically this reference orbital occupation eta naught to be 1/2. So because at 1/2, you get the correspondence between the slope of the nonlinear trend and the slope of the linear trend. And this can serve as reference to determine what should be the slope of the Koopmans linear behavior. And if you take the difference between the two, like we did for the Hubbard functional, what you obtain is this pi deviation from linearity for a given orbital that is nothing else than the integral of the reference orbital energy minus the energy that you calculate along the increase of the frontier orbital number. Okay, so that's what we obtain. And this is what you need to add to the DFT functional to be able to correct for self-interaction error in the same way that you add a U parameter, a U correction to go and correct the non-piecewise linearity of standard DFT functionals. So an important caveat is that we need also to take into account the effect of self-consistent relaxation. So as you remember, in the expression of the U, we had a dielectric constant that was this nonlinear operator that was essentially capturing the effect of orbital relaxation and screening. And so we need also to pay close attention to this orbital relaxation effect self-consistently. So essentially, if you start from an orbital of 1 and you ionize the system, you're going to get an energy deviation from the piecewise linearity that is quantified by this pi. And I put here because it's for frozen orbital, it's unrelaxed. So for unrelaxed orbital, keeping the orbital fixed at the what they are at the minimum of the full occupation, you get a given deviation. But if you now let the system relax as you ionize the system, what happens is that you obtain a deviation from piecewise linearity that is actually smaller than the unrelaxed case. And the ratio between the two is what we call the screening parameter, alpha, that captures the effect of this orbital relaxation self-consistently. And the correction that you need to have is not only the sum of the pi terms, but the sum of the pi term multiplied by the screening parameter to be able to theoretically capture the relaxation. And this pi parameter is typically between 0 and 1, meaning that it downscales the correction that we have in Koopmans. So then what you can do, and that's something that is very important, is that the derivative of the energy with respect to the density matrix gives you the Hamiltonian. And this Hamiltonian now becomes orbital dependent because the correction that you have depends on the orbital, because for each given orbital in the system, you're calculating a different deviation from linearity. And as a result of that, you switch from an effective field approximation in which the effective field applies to all of the orbital to an approximation in which each orbital has a specific Hamiltonian that essentially removes the self-interaction effect, removes its own contribution to the effective potential. The outcome of that is that now you have a formation that is not rotationally invariant, meaning that the Lagrange multiplier matrix that you have is not Hermitian. It becomes Hermitian at the minimum. And at the minimum, what you can do is then to diagonalize this Lagrange multiplier matrix in order to obtain the canonical orbital, the delocalized states, and the energy that describes the band structure of the system. So there's an extra step. You not only need to minimize and get the orbital energy like in DFT, but you need to diagonalize this lambda matrix at the end of the minimization. And this is the cost of having a Hamiltonian that becomes orbital specific and a formulation that is orbital dependent. So that's the key difference between what we do in Koopmans and non-Koopmans formulation of orbital interaction. So some results. So here you can see the situation for the unrelaxed Koopmans when I don't have the alpha, and the relaxed Koopmans. So essentially, it's hard to see here, but if you plot just the corrective part of the energy, you see that the LDA will have a significantly overestimated curvature that if you apply the Koopmans correction without relaxation, you're going to get an overestimation of the correction. So instead of being piecewise convex, you obtain an energy that is piecewise concave. And if you then rescale using this alpha parameter, whose calculation requires you to do a finite difference calculation or using linear response theory, like will be described in the next talks, you essentially are able to remove that spurious nonlinearity that affects localization, band gaps, and the shape of the density of your orbital. And as you can see here, the ionization potential, that is the energy of the frontier orbital, does not depend on the occupation of that orbital, meaning that you have effectively removed self-interaction errors. And as a result, also you can perform that diagonalization that enables you to calculate the energy levels, and you can see the nice correspondence between experiment and theory as you move from DFT to the Koopmans implementation of the semi-local functional on a par with self-consistent GW, in that case for that G2 molecular reference data set. So another important validation was also the calculation of full electron spectra. So we already know that the peaks of the spectra should be correctly described because we are specifically corrected in order to ensure that the energy levels fulfill that condition of self-interaction, not including self-interaction, meaning that essentially the energy of occupied state will not be overestimated and the energy of unoccupied state will not be underestimated. But we also wanted to see if we can calculate the intensity of the spectra that is tightly connected with the shape of the orbital. So this is a transition matrix element between two orbitals, the initial orbital and the final orbital. And if you don't correctly predict those wave function, you're not going to be able to calculate the correct intensity for the spectra. And you can see here that we did fairly well in predicting the photoemission spectra on the entire energy range for those fullerene donors that are relevant for organic photovoltaics. So we're very encouraged by these results, but the question remains of how can we apply this to extended systems? And the reason why it's not so trivial to be able to apply Koopmans to extended system is because we need to calculate that orbital relaxation parameter alpha. And we were doing that using finite difference. So essentially, you remove an orbital from the system and you observe the relaxation. And then you can calculate the rescaling that you need between the unrelaxed pi parameter, the deviation from piecewise linearity, and the relaxed one. And if you do that for an extended system, this entails being able to calculate a charge defect in an extended solid, which is a non-trivial problem to address. But thankfully, thanks to linear response, it is possible to directly calculate this alpha parameter, calculating the derivative of the energy as a function of the occupation of an orbital self-consistently using perturbation theory. And you can see that the result that we obtain in that case are fairly consistent with delta SCF results that we carry out for increasing large molecule. And it's also in close agreement with both Popper cluster and experiment. And this was initially implemented by Lin and Nguyen, that was the first to put that framework of linear response to calculate orbital relaxation, and then further developed by Nicola Colonna, Edward, and Ricardo. So we can also apply this to solids, and again, if you use GGA, you have this underestimation, and when you apply Koopmans or other flavors such as the Koopman integral formulation that Andre's going to talk about, you get this beautiful agreement between experiment and theory for calculating the band gap of semiconducting compounds. So really, again, here, the formulation necessitates orbital relaxation, linear response, and you will see also the implementation of this using Vanni functions. So to conclude, I would like to briefly mention this recently published paper. That was really the work of Edward, Lynn Scott, Nicola Colonna, and Ricardo. And I really want to thank you, and I really can measure the effort that they put into this implementation to be able to release that to the public. So I would like to very much thank them for this. So I would like also to thank the student that carried out all the works. I mentioned the work of Simon Gélin, Nicole Kirchner, Julian and Quinn were the people that applied the UMD, the initial benchmark, on which we have built a better understanding of the about correction to band gaps. I would like to thank Vincent, the one that did the high throughput computational screening, Wen Zhao and Sedao Turak that also contributed extensively to this work. So this is it. So for the introduction of the basic concept, I hope you remember what was told to me by Matteo, that concept of piecewise linearity and the Hubbard model, from which we can build then the Koopmans correction. I'm very grateful to Andrea Ferretti, who has been very creative, very insightful in improving many aspects of the implementation, especially when it comes to make the connection to spread-type functional. This is what he's going to talk about, and all of this idea of canonical minimization and be able to calculate the band structure, and Nicola Mazzari for pushing this idea over the last 15 years. So it has been a long journey, and obviously Nicola, Edward for bringing this idea to fruition. So thank you very much for your attention. I'll be very happy to put that.
Thank you very much. Question.
No, I wanted to ask, so is it correct to say that the Koopmans function and the KI they don't collect the total energy?
So in the KI flavor, yes, it's correct. Essentially what you have in that case, you exactly match the total energy at integer occupations. You don't correct the total energy for integer occupations except for fractional occupation. So that's how, but KIPZ does. I mean, there are some flavors that.
No, yes, but my question is, so do you think it is? I mean, it is a contradiction then to say that the KI corrects self-interaction, or so do you think it's a problem or an advantage? So this is my point.
Yeah, no, it's a very, very good question. So if you trust the DFT energy at integer occupation, you use KI, you will not change them. What you're going to change though is the derivative of the energy in the vicinity of integer occupation. So it's going to change the band gaps. Essentially, it's a rigid shift on the orbital energies that you apply, and that can be an approach that you apply in that case. You can also apply KI on Wannier orbitals. So in that case, you trust the Wannier orbital to relocalize the orbital, and then you apply the KI in the second step to just calculate the shift in area. And this is very similar to what my and co-worker have been doing. And that's something also that is implemented in that case. So you cannot just rely on KI to localize the orbital and correct the localization, but you can correct the band gap. So it's a partial correction, but it can be advantageous from the point of view of computational efficiency if you use it on top of an orbital. So I hope I answered the question.
Yeah. Thank you very much.
Well, thank you for your captivating talk. It was truly a delight to listen to. So I have 3 questions, but one was very close to what the last bit left. So the first one is kind of logistical. You mentioned this process where you start from a large potential number of compounds which you examine, and then you end up with a couple of dozens. So could you please go back to that?
Yes, of course.
Just explain the process a bit more thoroughly.
Absolutely, yeah, I'd be very happy to. Let me see. So Nulla, I guess this is what it means. that I can guess.
Yeah, with the
Yeah, so yeah, it's an 8-step process. So the first 3 are really computational. So we chemical stability. Here we do a DFT calculation, like no correction, but we rescale the criteria. So we know that there's a 40–60% underestimation of the band gap, so we take this into account. Then here the band alignment. This is done by estimating the flat band potential, essentially the energy in the middle of that gap, using geometric means of atomic molecular negativity. And all of this is experimental, so our colleagues will check the toxicity, whether or not the material can be synthesized. And here we apply for the few last compounds, the DFT plus U method, and the Koopmans also recently with Nicola Colonna. And this is computationally more demanding than DFT because you need to take into account to do the linear response. But once you have that, then you can propose candidates that are synthesized by our colleagues, and then they can check and perform experiments on those compounds. And we obtain, so I guess 6 of the 11 photocatalysts that we proposed were actually shown to produce hydrogen in this paper. And
how, I mean, I guess all of this is automated. How do you go through the synthesis?
Oh yeah, so this is manual. This one we ask our colleagues, and they do that routinely. They check the literature to make sure the material can be synthesized. Nowadays, there are a lot of natural language processing method that enable you to do that with machine learning. So we would love to be able to do that with machine learning and with all of the development, ChatGPT, and this type of technique. It would be extremely valuable to have that here. Absolutely.
Okay, the second question should be a bit closer. How would you say this scales with the system side as compared to plain DFT?
So here, what we have is orbital dependent. So you need to calculate an Hamiltonian that is different for each of the orbital. So this scales as n to the 4th in principle. You have an extra layer compared to the cubic linear scaling, but the prefactor is quite small compared to the prefactor that you have in hybrid functional and in GW. So it's the cost is in between what you have for hybrid functional and what you have for DFT. They're actually in the appendix of the paper of Nicole. There's a benchmark where I think it's a factor 4, even if you include all of the self-consistent calculation of the U parameter. So that paper has that detail in there. Thank you for the very nice question.
Very nice. Importance to apply correction every state, right?
Yes.
But to include the band gap, I would expect you just need correction to the edge states like top of the valence and bottom of the conduction, which are influencing the band gap directly.
Yes.
Those states which are deep, I think, even if you leave it at the LDA or the GLO, should not matter. What do you say?
Yeah, no, I agree with you. And whenever you apply the U, we check first for what are the frontier states, and we apply the U specifically on those ones. And for the sake of efficiency, you could do the same with Koopmans. So essentially, Koopmans and Hubbard are brothers. Whatever you do with one, you might also do with the other. So there's a lot of similarity in the way you can apply those two. So that's what we did here in Hubbard frontier orbitals. Unless you have a very good reason for it, like in transparent conductor, you also need to know the deeper energy level beyond the T2G state. But in general, I would say that you can get very good band gaps with just this correction. Thank you.
Thanks a lot for the nice talk. So whenever I guess you hear an orbital dependent condition, maybe the natural question is how dependent on your projectors and the way you define your orbitals. How is your theory dependent on that? And what you would think are the best ones? I mean, maybe you already hinted to functions and you think would be the best description we could have to define the theories?
Yeah, no, I think the observation is that a lot of time when you look at the final orbitals, the variational orbitals that are obtained by Koopmans, they very much look like Vanier function, with the caveat that they are not maximally localized Vanier function in the sense that they typically only involve a linear combination of occupied orbitals. So you need to have this separation between occupied and non-occupied. And I always wonder that if you use Vanier function fully maximally localized Vanier functions, and then if you allow yourself to minimize with respect to linear combination of those Vanier functions, would you obtain essentially the Vanier functions that only span the occupied manifold? So I think Vanier functions are great, but you can also probably look at linear combination of Vanier functions as an efficient way to implement the Koopmans function, but I think Nicola is probably already thinking about this type of thing.
No, it's okay. I just want to wonder. I mean, in our function, you select the nine function and use harmonic order from the two potential. In this framework, I mean, the minimization of the energy provides you the right when you use the right connection. So in that respect, in principle, no, I mean, right. So you have a function to minimize it, you get set of localized orbital when you place the principle there's no thing to the other. So it's the minimization of energy that's really when there are carriers at the eye, you might have more freedom, but in principle, there's no. It's the minimization of the energy that's different.
So no, thanks a lot. Yeah, I didn't understand this aspect of the question. Absolutely. Yeah.
Yeah, thanks, man. I was just wondering if indeed you can do, let's say, tabular, so if you can also correct the total energy of the systems, because you know that I mean, it works very well GA, but
Yes.
several times, especially in transition methods, we are not so accurate.
Yeah. So I mean, here we're initially happy to just preserve the structures that you obtain from GGA. But in some cases, yeah, GGA underbinds, LDA overbinds. And the hope is that by correcting the location of the orbital, you can correct the bonding and get better structures. So I think there are several examples where this is the case. I don't have them specifically here, but in the molecular data set that were presented, there's a comparison of the bond lengths that you obtain by Koopmans. And in general, you either preserve or improve the prediction of the bond length. So that's something we have not looked systematically in tough cases, but it would be very nice to indeed look into this. Thanks for the relevant question.
Question? Now, let's thank